Hi everyone, and welcome back. We're now going to get into the meat of the first unit of a typical non-AP physics course. In fact, even an AP physics course as well. Kinematics. Kinematics is the study of motion. And in this next series of videos, we're going to examine kinematics from a graphical standpoint, how we can represent motion via graphs, and upon being given a graph, figure out what we can discern about what's going on in the motion. So naturally, this is an experimentally based course, and especially an experimentally based unit. So a nice little Calvin and Hobbes clip here. So Calvin's asking his mom a bunch of questions that are easy for him to verify for himself. He realizes a pattern and then tries to get at what he really wants. But unfortunately, it ends up failing for him. So I should note that if you happen to have downloaded a PowerPoint of this video, then make sure that you're actually using it in slideshow mode on a PC with Microsoft PowerPoint. Otherwise, animations and stuff like that won't get rendered correctly. So as I mentioned before, kinematics is the study of motion, including the forces that bring that motion about. At least that's one way of thinking about it. Other ways of thinking about it, you can just pretend that those forces don't exist and group those in with dynamics. I usually think of dynamics as something that involves some sort of energy and relationships between motion and energy. But other people consider dynamics simply to be studying how motion is affected by forces. It really just depends on who's giving you the definitions. Either way, what we're focusing on right here is kinematics by anybody's point of view. So consider a number line. Remember, in a number line, toward the right is the positive direction, toward the left is a negative direction. But what we will often focus on will be a position versus time graph, where we imagine that the number line has been rotated 90 degrees counterclockwise and pasted as the vertical axis of a graph. So position is given by the symbol x most of the time, at least for us. So it's given by the symbol x, at least when we're dealing in one dimension. If you're dealing with multiple dimensions, it might be given by the symbol r, or r vector. Now time is on the horizontal axis. So notice this is not a y versus x plot. This is an x versus t plot. Don't call it the y-axis, especially since x is graphed on the vertical axis. In other words, y is just not going to be represented in a position versus time graph, because we're representing just horizontal motion. So just keep that in mind. Now, let's look at an example of how we might graph something like this. So a man steps out of the house and walks to the mailbox in front of the house. And at the mailbox, he pauses while fumbling through the mail and turns and walks back to the house, pausing halfway there to smell a flower. And after smelling the flower, he runs into the house. So how would we represent this? We are going to pretend, since we weren't told otherwise, that the mailbox is situated to the right of the house from our point of view. So first, we're going to graph the house at the origin. So we're going to assume that this house isn't getting swept away in a flood or a tornado or anything like that. So it's not moving. As time goes on, the house stays put, which means that its position doesn't change, but time is just constantly streaming onward. The mailbox would be, well, we said that the mailbox is to the right of the house. That means that it's at a more positive position. So since position is graphed vertically on this graph, that means the mailbox is going to be graphed above the house. And again, we don't think that our mailbox is going to be moving, so it's just a horizontal line. Meanwhile, I'm going to be really pedantic here and throw the flower in there as well. It says the flower is halfway between the house and the mailbox, so we put that about halfway in. So the man steps out of the house. In this case, our time is kind of arbitrary. Also, I should mention that I was a very bad physics student in this example, and I didn't label my axis. I should have labeled the time axis going horizontally, and I should have labeled the position axis going vertically. So in any case, we don't know what time this happened at, but we're going to say the man stepped out of the house and probably paused, and as soon as the man started walking, that's when we actually started our watch. So we started graphing the man's motion as soon as he walked, and he walks toward the mailbox and then pauses while fumbling through the mail. There's the pause. and then walks back to the house and pauses halfway there to smell a flower. See, there's the pause again, and smelling the flower, and then after smelling the flower, maybe it gets stung by a bee and runs back into the house. So there is our graph, our position versus time graph in red for the man's motion. Now, you might want to ask yourself, it's instructive to ask yourself, what features on the graph denote the pauses? What distinguishes the direction of motion? And what distinguishes running from walking? So in the case of the pauses, remember that when something's not moving, time is still going on. Just the position isn't changing. Well, position is graphed vertically, so if the position isn't changing, then the vertical part of the motion is not going to change, but time goes on. So a pause would be denoted by a horizontal line segment. So we have that here at the mailbox and here at the flower. And then the direction of motion. Well, going away from the house, we said that the mailbox was toward the right, so the person's going toward the mailbox. No, the graph of the motion is now going to be going upward because more positive denotes upward, because that's toward the right is more positive. Now going back toward the house, that's going to be toward the negative direction, because that means, like, if the mailbox is in the positive direction, or at least more positive than the house, then walking back from the mailbox to the house means that he's going in a less positive, i.e. more negative direction. In other words, what distinguishes the direction of motion? It's the sign of the slope. And then third, what distinguishes running from walking? That's going to be a steeper graph. A steeper graph is going to be moving more quickly, because that means that there is a larger change in position over the same amount of time, or the same change in position in a shorter amount of time. That's what a quick motion would mean. Now, let's consider another example. You have a flea watching a yo-yo pass him while resting on a drawer. That is the midpoint of the yo-yo's motion. Create a position versus time graph for this scenario. If the flea sees the yo-yo passing at constant velocity on the way down, and the yo-yo pauses at the bottom, and then travels past the flea on the way up to the yo-yo master's hand. And then the yo-yo's motion never ceases as the yo-yo master throws it down again. And on the way down, the string gets twisted, and the yo-yo stops at the exact height of the flea. And then after a moment, I guess it gets untwisted and drifts down to the end of the string. So how would we represent this? So in this case, I actually was a good physics student, and I labeled my axes. And notice this time I actually called the vertical axis the y-axis, though the horizontal axis is definitely not the x-axis, it's the time axis. So the reason I called the vertical axis the y-axis, because the yo-yo is moving in the vertical direction. So I figured, might as well. After all, why not? That's the initial vertical position. Whatever. Okay, so again, I decided to be a little pedantic here, and I graphed the yo-yo master. So there's the yo-yo master, at least the yo-yo master's hand, kind of toward the top. And you might be able to see a very thin green line in the middle of this. That is the flea watching in the middle of the dresser drawer. And then we have the yo-yo. So when we first started looking at this, the yo-yo was on its way down, and then it paused. So there's that horizontal line segment where it paused, and then it went back upward at the same speed, and then the yo-yo master threw the yo-yo down. Well, throwing, that's probably going to be faster. So notice we have a steeper slope here. And then it got stuck, and then slowly drifted down. Not so steep of a slope. So that was the situation here. Another example. We have a cat, a mouse, and cheese. So let's consider this picture with a cat and mouse playing together. The cat has baited the mouse with a piece of cheese resting in front of himself. So the following happens. While the mouse slowly walks toward the cheese, but a quarter of the way to the cheese, he gets spooked and runs back to the safety of the small rock. And then, after that, goes halfway to the cheese and gets scared and runs back to the small rock. And then after that goes 3/4 of the way to the cheese, gets nervous, and then runs 2/3 of the way back to the rock before changing his mind, running toward the cheese faster than before, grabbing the cheese and running back to the rock a little slower. The cat begins to chase the mouse, and the mouse begins to move as fast as yet by taking big jumps toward the rock. pauses and continues a quarter of the way past the distance of the rock and realizes that the cat was actually being chased by a dog and then walks back to the rock. So the question is, what should a graph of this situation look like? What should a position versus time graph of this situation look like? So maybe take a minute to pause the video and draw out a position versus time graph and make it as illustrative as possible. So now, assuming that you have taken a minute to pause, let's take a look at the answers that you should have gotten. So here we go. I have my x-axis, my position axis, going vertically as before, and I have the time axis as before going horizontally. And again, I decided to be a nerd and I graphed a bunch of things here. I graphed the rock doesn't move, but notice that I have the rock at the top of the graph. Why? Because if you look back at the example, the rock is toward the right. And I have the mouse. I actually had the mouse kind of with the graph. I probably should have had it starting a little bit above it, but whatever. In each case, by quote behind the rock, I guess I kind of mean with the rock. The cheese, I had the cheese at kind of the origin, so to speak, and then the cat is behind the cheese. So notice, since the cat is to the left of what I'm calling the origin, that means its position is negative. Now, you didn't have to do that. You could have put your cat initially at the origin. So anyway, the mouse goes a quarter of the way to the cheese slowly. So notice that's not a very steep slope, and that's a quarter of the way, and then runs back to the safety of the rock, and then goes halfway to the cheese, runs back to the safety of the rock, and then goes 3/4 of the way to the cheese, turns and goes back 2/3 of the way. Well, 3/4 of, well, that's why I made it 4 units, and 2/3 of 3 units is going 2 units back, and then runs faster than ever before and grabs the cheese. Notice now I was really a nerd here, and I have the cheese moving along with the mouse. So first the mouse isn't going quite as fast, but then thinks the cat is chasing him and starts making jumps. And you know, when you make jumps, there's this temporary pause before your next jump. So again, I was being a dork, and I put those little temporary pauses there. And then the mouse went further than the rock, 1/4 of the way further than the rock, and then saw that the cat was being chased by a dog. There's the cat going after, and then notice there's the dog coming right there, and then the mouse slowly goes back to the rock and enjoys his cheese. Now, I guess I could have been a little cruel here and had the dog's slope being noticeably steeper than that of the cat, and then simply had the cat disappearing at some point, and then only the dog. But anyway, that's how we would graph this type of problem. Now, if you want further conceptual practice on this, we'll try to remember to post the link to this website that was created by Tony Wayne, where he has this practice involving a ladybug's motion across a number line, and you would practice graphing its motion in that case, so you can get some more practice that way. Now, we need to make some definitions. Let's try to extract what we have learned from these graphs and see what else we can see how much farther we can go. Now, as we mentioned before, the symbol for position is x, and it's a sense of an object's location. Now, I should mention that sometimes people confuse position with displacement. Displacement is defined as a change in position, final position minus initial position. Whenever we say change in something, we mean final minus initial. So displacement would be written as delta x, delta meaning change in, which means, again, final minus initial. But if we say that the initial position is 0, then delta x is equal to x. And in a lot of cases, we will call the initial position equal to 0. So just read carefully the problems that are being given to make sure that you understand what's what. Now, time is given by lowercase t. By the way, typical units of position are meters. That is the SI unit of position. That's what it will be like on most of the tests that I give students in my classes. Typical units of time are seconds. And The way that we will often think of time, at least when we put it in our equations, is actually more as a change in time, really a delta t. But a lot of times we just get tired of writing deltas in front of our t's and we just put it as t. Now, since we've talked about fast motion and slow motion, that brings to mind, well, what about the rate at which an object's position changes? That is called velocity. And it's how quickly you change in position. And whenever you hear the term quickly in physics, you should often kind of think of dividing by time or dividing by a time interval. So that would be delta x over delta t, or assuming that our time started at 0, which it often does, just delta x over t. But be careful, whenever you see this equation, you should really be thinking this t is actually a delta t. And again, if we started at a position of 0, then that delta x can be considered to be an x. Now, what can we make of this? What can we actually do with this? How can we solve problems with this? Well, we need to come back to slopes. Remember what a slope is? Of course you remember what a slope is. You remember it as being rise over run. But what does that mean? Rise is the change in your vertical coordinate, or your vertical quantity. So delta vertical quantity. What is run? Well, run is change in horizontal coordinate, so delta horizontal quantity. So if we have a position versus time graph, rise over run, if we were trying to take a slope of that, would be delta x, the vertical stuff, divided by delta t. So delta x is the change in our vertical part divided by delta t, the change in our horizontal part. There we go. So there it is in that formula. Well, wait a second. Apparently, that means that velocity is the slope of a position versus time graph. Or I guess, to be more precise, instantaneous velocity is the slope of a position versus time graph at a particular point. Average velocity would be the slope between two points situated at some place apart on a position versus time graph. That would be average velocity. So for 2 points on an x versus t graph, the rise is delta x and the run is delta t. We can go further from that. As we will discuss in a future video, acceleration is how quickly you change velocity. So if you happen to have a velocity versus time graph, acceleration would be the slope of that. In fact, you can even go further. There's something called jerk, which is the change in, it's how quickly you change acceleration. In other words, the slope of an acceleration versus time graph. And there's even something called jounce, which would be the slope of a jerk versus time graph. But we're not going to get into that. In fact, we're rarely even going to get into jerk. Okay. So, a little pictorial device for you, in that sense, is that let's say you have an x versus t graph. Well, if you want to take the slope of that, that gives you a v versus t graph. And if you want to take the slope of that, that would give you an acceleration versus time graph. If you want to take a slope of that, you'd get a jerk versus time graph. For now, though, we are just going to focus on position versus time graphs and velocity versus time graphs. So let's practice taking some slopes. So let's say you have a whole bunch of straight line segments here. So the question would be, how would you calculate the slopes of these things? So the idea here is that these are drawn with the intent that the endpoints of these line segments are actually crossing easily identifiable grid lines on the graph. So in other words, let me just look at graph B right here. So the leftmost point in the line segment on graph B would have coordinates of 5 years, comma, -2 yards per minute. And the rightmost point would have coordinates of 21 years, comma, 5 yards per minute. How did I get that 21 here? I mean, the 5 is easy to identify because you just go down here to the 5, and the -2 is easy to find because you notice that each of these horizontal lines goes up by 1 yard per minute on the velocity part. However, what about the horizontal axis here? Well, there are 10 segments here, so 11 lines, so 10 divisions, so to speak. So 10 divisions, but going from 5 years to 25 years. So if that's that's a change of 20 years over 10 divisions, so that means that each time division is worth 2 years. So I need to go down to here, so I had 25 years over here, that would be 23 over here, 21 over here. So 21 years, comma, 5 yards per minute. So if I wanted to take the slope, those would be the points that I would use. Now, let's go through an example of just finding the slope of one of these line segments. Let's look at line segment G. So in line segment G, well, how do we find the slope? How about we take 2 points that are far away from each other and on easy to identify points on the graph. In other words, how about these 2 points, the endpoints? So, well, what is that first endpoint? The coordinates for that first endpoint, well, you can see that that's at 3 hours, and again, 10 divisions with a change of 30 feet per night. Weird velocity units, but whatever. That's going to mean that each division going up is worth 3. Each division going horizontally is worth 0.1, because you're going from 3 to 4, which is a change of 1 hour. So the first point is 3 hours, comma, 57 feet per night. And the second point down here, that would be 3.1, 2, 3, 4, 5, 6, 7, 3.7 hours, and up 30 feet per night. Okay, so we've identified 2 points on our graph that can aid us in calculating the slope. So let's do it. Apply the formula for slope. Remember, it's rise over run. Well, the rise here is, again, it's always change in vertical stuff. The run is change in horizontal stuff. So, well, what's vertical stuff? Apparently, vertical stuff is velocity, so I just write that as delta v. Horizontal stuff is delta t, time. Well, what does change in mean? Remember, it means final minus initial. So, the final velocity, let's read, oh, that would be our final point. It's right here, 30 feet per night. So that's what we plug in there. Minus initial velocity, well, that would be the velocity from our initial point, well, 57 feet per night. So that's what goes in here for v initial. Divided by, well, final time minus initial time. Final time was 3.7 hours. Initial time was 3 hours. So you work that out, and you get about negative 38.6 feet per night hour. Yeah, those are really funny units. How did we get those units? Well, we just took the vertical units and divided by the horizontal units. Feet per night divided by hours is feet per night times 1 over hours, or feet per night hour. Just don't try using those units as your final units on some chemistry problem or something like that. Okay, so hopefully that was a clear example of how we would calculate a slope. Now let's figure out what we can do with this stuff. We already mentioned that velocity is the slope of a position versus time graph. So what we can extract from that is if you take any position versus time graph, even a graph that has curves on it, ooh, curves, scary, ooh, well, you can still identify 2 points throughout those curves and just draw a line between those 2 points and figure out the slope of that line. Well, what is that the slope of? Well, it's an average slope between the 2 points. We call that average velocity. In fact, the definition of average velocity between over a time period delta t is the change in position divided by that time period delta t. So, how would we work that out here? How about calculate the average velocity from 2 seconds to 3.6 seconds? Well, we need to figure out where our points are. Well, there's the point at 2 seconds. Apparently the position there is 0. And there's the point at 3.6 seconds. So apparently the position there is 6 meters, because notice we're going up by 2 meters for every division up here. So we have our points. We've identified those points. So we're going to shove those points into our equation for slope. Remember, solving problems, you start off with what you're given. Well, we also need to apply a definition here. So we're going to tell the world that we are applying the definition of average velocity as delta x over delta t. So just x final minus x initial over t final minus t initial. And we already wrote down our points by circling them and writing out their coordinates from that previous graph. So that x final was 6 meters, that x initial was 0 meters, but 0 times meters is still 0. And time final is 3.6 seconds. The initial time was 2 seconds. So our delta x was 6 meters, our delta t was 1.6 seconds, and dividing those through ends up giving you a an average velocity of 3.75 meters per second. So that's the average velocity going back to this graph. So just going from here to here, if somebody said, oh, the person's at 0 meters at a time of 2 seconds and 6 meters at a time of 3.6 seconds, well, that means their average velocity must have been 3.75 meters per second. So if the speed limit was 3 meters per second, you know for a fact that the person was definitely speeding over that time period. So that's one way that police officers can tag motorists and determine that, hey, they were definitely speeding. If they don't happen to have a radar gun with them, they can just follow them and say, like, hey, they went through a mile marker at a certain amount of time, and then time them how long it takes to go through the next mile marker. And if the speed limit is 60 miles per hour and it took them less than a minute, then they can conclude the person was speeding. Same thing here. Now, I should note that the average velocity, which is basically an idea of, like, if you were to average out the slopes on that graph, that is very different from the instantaneous velocity. Instantaneous velocity would be like, okay, remember that was a curve that you just saw? Well, how would you calculate the instantaneous velocity at a point in time? In other words, how fast are they going at that particular time? What would a radar gun read if it was to be bounced off of that person at that particular time? Well, the idea is that if it's a straight line segment, well, then the instantaneous velocity anywhere on that straight line segment would just be given by the average velocity for that line segment. However, if it's not a straight line segment, if it's a curve, then you'll have to just pay attention to a future video, in which we will discuss how to do it if there are curves. So remember our pictorial device, the slope of your position versus time graph being velocity, slope of that being acceleration, slope of that being jerk. Well, for now, again, we're dealing with constant motion, meaning that the acceleration is zero. Or sorry, that the acceleration is constant. And for now, so far, the acceleration has been zero because we're pretending that our line segments on position versus time graphs are going to be straight. Now, it is possible to make a plot of a velocity versus time graph from a position versus time graph. In fact, if you know calculus and you happen to know the functional form, like somebody tells you x of t is equal to like 3t cubed minus 2t squared, etc., then you could just take a derivative and plot the derivative. But this is a non-calculus based course, so you are going to be expected to determine the slopes of the lines on a graph. But remember, a straight line has constant slope, and that's what we're going to be using here. So let's say that you have this position versus time graph in this particular example. And I'm not putting units on either of my axes, so we don't know what units these are. Maybe it's feet per second, maybe it's meters per second, miles per hour, or whatever. Or sorry, this is a position versus time graph, so maybe the units are feet or miles or whatever. And maybe the time units are seconds or hours or whatever. We just don't know. So, point is, though, you can still do the math, just you won't be plugging in units. In the last example, we plugged in units because we knew what the units were. When you know what the units are, you got to plug them in your calculation and in your answer. So in this case, we don't. But we still notice that we have a bunch of straight line segments here. So you can draw a velocity versus time graph from this position versus time graph. So like good physics students, we are going to put axes on our graph, and we're going to do the same thing for our velocity versus time graph. And don't forget, slope is rise over run, which means change in vertical over change in horizontal. Well, how do we figure out these changes? So we noticed that on the first line segment, we went from a position of 2 to a position of -6. That's a change in position of -8. Over what time did that happen? That happened over a time of 2 units of time, whatever our units are. So there's our time. So that slope is going to be, well, change in vertical over change in horizontal, rise over run, -8 over 2 is -4. And that's -4 everywhere between a time of 0 and 2. Not just at the beginning, not just at the end, not just in the middle, but at every single other point, at a time of 0.35, at a time of 0.717, etc. Everywhere between a time of 0 and 2, that slope is -4. In other words, that velocity is -4 units, whatever those happen to be. Between 2 and 3, well, that's a change in time of 1, but we ended up going up by 3 during that time. So that's a slope of 3 everywhere between a time of 2 and 3. So the velocity everywhere between a time of 2 and 3 is 3. Why everywhere? Because it's a straight line segment. If it was a curve, you wouldn't be able to do that. And we can do the same thing for the rest of the graph. So now the idea, now that we have written down our slopes for each of these line segments, and we know that each of these slopes is a constant slope throughout that time period, we can now graph the velocity. Well, we're going to say, okay, for that first line segment, the slope was -4. What's slope of a position versus time graph? Oh, it's velocity. Well, it's -4 everywhere, which means the velocity is -4 everywhere from 0 to 2. So that's -4 everywhere from 0 to 2, a horizontal line on the velocity versus time graph. Yeah, that's right. If the slope is constant, then that means if you're graphing slope, it's just going to be a flat line. Because after all, the velocity is constant. The position's changing, but the velocity is not. What about the next part, from 2 to 3? Well, that's a slope of 3. Unfortunately, this animation didn't quite line up. I actually lined it up right before I started this presentation, but I guess it didn't end up going through for whatever reason. There's PowerPoint for you. But in any case, yeah, from a time of 2 to 3, that slope was 3. From 3 to 4, that slope was 0, so we're graphing 0 down here. Yeah, you can barely see that thin red line there. Hey, made it funny. And then from 4 to 5, that slope is constantly 4. From 5 to 6, that slope is constantly 0. From 6 to 7, that slope is constantly 3. From 7 to 8, that slope is constantly -2. From 8 to 9, that slope is constantly -7. And remember, whenever I said slope here, I meant velocity, because the slope of a position versus time graph is, what is it? Yeah, velocity. Ta-da! And then if you really want, you can make dotted lines between these things. Okay. So, what about displacement? Displacement is the change in an object's position. The change in an object's position. So again, what does change in mean? It means final minus initial. So displacement is final position minus initial position. So if your graph is a position versus time graph, if they're asking you to calculate displacement, you can just read off the initial position and subtract that from the final position. Like in this example, calculate the displacement from 5 seconds to 25 seconds. Now when they say calculate, that means show your work. Even if it is trivial work, you still need to show it. Calculate the displacement, well, that means you're going to need to use the formula for displacement. Show the formula for displacement. So here's the graph, and we're going to pick off the points at 5 seconds and 25 seconds. Well, at 5 seconds, the position was 9 meters. At 25 seconds, the position was 4 meters. So what's the displacement there? Well, delta x equals x final minus x initial. So there's showing your work. Delta x equals x final minus x initial. There's the formula. Equals, well, plug in the values. X final was 4 meters. X initial is 9 meters. 4 meters minus 9 meters is -5 meters. So to get all of the points on this, you would have to show the formula, check. Show the plugging in of the values into the formula with units, check. And show your final answer with the correct magnitude, sign, and units, check. So -5 meters. So that's how we would solve a problem like that. Later on, we're going to get to another way of calculating displacement from the area under velocity versus time graph. We're going to get to that later. So you might think, well, I thought distance was equal to rate times time. So isn't distance, delta x, just that distance traveled? So it is, assuming that you're moving at constant velocity. If you're not moving at constant velocity, that's something that we're going to get to in a future video. But for now, we're assuming straight line segments on position versus time graphs, and in that case, we can just say delta x is equal to v times t. So that's something really that we have extracted from our graph, from our understanding that velocity is the slope of a position versus time graph. In other words, if v is equal to delta x over delta t, if it's a straight line segment, then just multiply both sides by delta t. That tells you that delta x is equal to v times delta t, or if we start at time 0, just v times t. In other words, rate times time. Let's look at an example. So if a car travels at a rate of 32 meters per second, a constant rate, for exactly 1 minute, how far does it travel? Well, write down your givens. And notice that I have converted to SI units because I'm planning to use this formula that delta x is equal to v times t. And I'm going to be plugging in units of meters per second for my velocity. Well, I know that I'm expecting distance units in my answer, like meters. Well, the only way those seconds down there will cancel is if I convert my time to seconds. So, quick unit conversion there, and then make sure we're plugging it in. In fact, we could have done that conversion in the problem if we were being really weird. We could have said, this is 32 meters per second times 1 minute times 60 seconds over 1 minute. In other words, actually shown the unit conversion in the problem. No, you don't need to do that. I mean, everybody knows that 1 minute is 60 seconds. Well, okay, Chantilly high school students might not know that, but we can make fun of them. So anyway, multiply 32 times 60, and you get 1920 meters. And if we want to be really cool, we will write this as 1900 meters because 32 meters per second is 2 sig figs. But if you didn't do that, that's fine. So at least for my students, that's fine. For our non-AP, non-honors physics students at our school, that's okay to do that. You don't need to worry about your sig figs, as long as you're being sensible about it. I mean, if you write out 8 decimal places after a number that already has 3 sig figs, and it's clearly not accurate for the problem, then yeah, I would be unhappy and I might take off a point. Okay, let's look at one more example for this video. Let's say you have a weasel that has stolen a chicken, sneaky, 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 from Farmer Bob, and it's running away with it at 3.74 meters per second. So if the weasel runs at that constant rate along a straight line, how long does it take to return with the chicken to its weasel hole that is located 18.2 meters away? So it's already away from the weasel hole, so its distance traveled is going to be 18.2 meters. Well, we write out our givens, just like before. We have our delta x, we have our v. So write the equation that you're going to use. Well, that's delta x equals v times t. But here we're being asked to solve for the time t. So t is equal to delta x over v. And now we plug in our givens. And also, yeah, notice that since we were trying to solve for t, we needed to divide both sides by v to undo the fact that the t was being multiplied by the v. So we plug in our numbers. We have 18.2 meters divided by 3.74 meters per second, and that gives us 4.87 seconds for that time. Notice that in plugging in our units, plug in our numbers with units, the units have worked so that the meters divide out. You have 1 over seconds, which is just seconds, so the units work out. If the units don't work out, then you've either done some bad math or you used a wrong formula. That's another good reason to plug in your units to make sure that you haven't made those types of mistakes. So that's it for our video at this point. We have shown how to graph position versus time and graph the motion of an object on a position versus time graph. We have gone through how to take the slope of a position versus time graph to find the average velocity over a time segment. We've noted that if the position versus time graph is a straight line, or at least a straight line segment between two particular points, then that would mean a constant slope, which means a constant velocity between those 2 points. And then from that, we've realized that, hey, since velocity is the slope of a position versus time graph, that is v equals delta x over delta t, then that means that we can get back our old kindergarten formula of distance equals rate times time, and say, okay, delta x equals v times delta t. So if you have any further questions, please drop them into the responses on the YouTube. And thank you all for watching.